Welcome to my first video on this channel. My name is Dennis, and I want to give you a short overview of the project I've been working on in the last around about 10 years or so, I think. And this is basically it. That's the current state of it. It's a homebrew computer based on the Zilog Z80 processor. And yeah, I've designed the system myself. This is the this is the current state after many prototypes. It's a homebrew Z80 computer system with a custom backplane in a modular construction. Each module serves an individual, a different purpose, and so it's easily extensible. And in this video, I just want to show you what I've achieved so far, what this little thing can do. Although it's not much compared to today's processors and microcontrollers, the thing is vastly underpowered. It's just for having fun. And having fun, before I get started, I just want to give you a brief warning. I am not a computer scientist. I didn't study electrical engineering, computer science, or anything like that. Everything that I show you in this video, everything that I've built, based on knowledge that I've taught myself over the past 10 years or so. And yeah, from reading data sheets, watching YouTube videos, reading forums, analyzing schematics from other computers, a lot of researching. So this is not an educational video, this is just for entertainment purposes. And I hope you enjoy it. So let's get started with the system. Over here you can see the chassis. It's a Euroc format with a custom backplane. It has a power supply in it which supplies 3 voltages, 5 volts, 12 volts, and minus 12 volts. And yeah, that's basically everything this computer needs. This computer has 4 modules. As of right now, there are more modules in development, for example, a sound card, which I'll show you in another video when it's done. The first module is this one. There's the CPU board, then there's the multi-IO board, the disk board, and the video board. Theoretically, you can expand this backplane further until there's until the physical limit where you can no longer sustain the clock frequency due to the length of the wire and stuff like that. Yes, however, let's get started with the first module. I'll pull this out and show you in a different view. Let's disconnect the serial cable and switch over to this view right here. It's a bit overexposed. Let me see if I can fix it. So this, as I've already said, is a Eurocard format. It's 100 by 160 millimeters in size, if I'm not mistaken. It has this 64-pin connector on the back here, which connects to the backplane. This has all the relevant data and address bus and control lines on it that I need for the peripherals to connect to this board. This board by itself is a single board computer. It can run completely isolated from the rest of the system. You have a footprint here for a barrel socket to connect 5 volts DC. Yeah, this was the first PCB that I've designed. Right here we have the Z80 CPU. At the moment clocked at 10 megahertz, but it's designed to be clocked at 6 megahertz. I've just tried to see how far I can push it, and 10 megahertz was the limit at which it worked stable. So that's where I've kept it so far. Right here we have 2 32K SRAM ICs for a total of 64K static RAM, 32K of ROM. I'll show you in a bit how this is all mapped into 64K of memory address space, programmable logic, glue logic to address all those ICs. Right here we have a counter timer IC with a quartz crystal as a clock generator of 1.8432 megahertz, which allows me to generate most common baud rates using this IC. And this then provides the clock for the RS-232 interfaces to the SIO IC, which is the serial I/O controller with 2 ports, one on the front, RS-232 DB9 connector with max 232 level shifters and an FTDI connector right here. Also has dip switches to set the baud rate, power and reset logic, and reset switch and indicators for reset, power, and system halt. Yeah, that's basically it. SIF socket with the EEPROM in it, containing my BIOS and all the necessary routines. And this whole thing is mapped into memory in the following way. Let me pull it up in KeyCard here. Here are the schematics, and you can see it's a bit complicated, but it's not as complicated as you might think. Here we have the CPU on the side, on the left. Here we have the 2 memory ICs, SRAM ICs, and 1 EEPROM. The way this maps is using this logic. The way this maps is that the upper 32K are always visible in the address space. The lower 32K are split into 2 16K chunks, and the EEPROM, which is also 32K, is also split into 16K chunks. So the EEPROM is always visible within the first 16K of the address space, and I can switch which half of the EEPROM is visible in the 16K address space, if it's the first 16K or the 16K, but it's also always visible in the first 16K of memory. And the SRAM is always visible in the second 16K of memory from address 4000 to 7FFF hex. And yeah, that's basically it. It has another feature. I can select, I can set the ROM invisible, so the full 64K of RAM are accessible in the address space and can be used by programs, for example, BASIC. So let's go back to the computer and have a look at the next board right here, which is the multi-IO board. All right, go to this view. Here we have the multi-IO board. This serves several purposes. This is just a quick overview. If you want to go into more detail, you can check out the schematics on my GitHub. Links are in the description. This one, as its name implies, serves I/O ports. For example, PS2 ports for mouse and keyboard with this 4042 style keyboard controller. It has 8 GPIO pins, speaker, a buzzer for peeping. It has an I2C interface, which is implemented in the PIO chip. The PIO chip also serves as an interrupt controller for all non-Z80 peripherals that don't use the interrupt mode 2 of the Z80. It has a real-time clock. It has an AM5911. Not quite sure. It has an AMD APU, which is suitable for arithmetic operations, and but I don't use it at the moment because the clock with 10 megahertz is way too fast for this. But it technically works if I run it at 4 or 6 megahertz, thanks to this counter IC, which is used as a clock divider right here. So I can set if I want to divide the system clock by 2, 4, 8, or 16. And this way I can use this APU if I want to. Haven't had the need for that yet. Maybe in the future at some point. It's just had it laying around, so I decided to put it on here. And that's basically all that's to this board. On all I/O boards, I use bus transceivers to put relieve a little bit of the load on the CPU I/O pins, and yeah, it makes it also easier to troubleshoot. And I always use those, almost always use those programmable logic ICs to do the address decoding, and glue logic for all those peripheral ICs, battery for real-time clock, and that's basically it. Yeah, some jumpers for setting the interrupt channel for the AM5911. I think it's 5911, I'm not sure. And jumpers right here, up here. Each peripheral board has those. I can set the base address of each board. So if I want to add another I/O board, I can change the base address of this board, and then I can address both of them in the same system, which is pretty useful for some tasks. For example, if I want more GPIO pins and stuff like that. All right, then let's go back over here. Put this back in. Have a look at this board, which is the disk interface board. As the name also implies, this provides access to several kinds of disks. CF cards right here in the front. It has an Intel 82C55 I/O controller, with which I access the 16-bit IDE bus with the 8-bit Z80 CPU. It has an IDE header for hard disks, drives, and it also has a floppy disk connector. The floppy part of this controller is not yet fully implemented. There's still some work that needs to be done, and I also need a floppy drive to test this with, but the hard disk part is working perfectly. Here you can also see some jumpers for setting the base address and configure the floppy interface as well as the IDE interface. But that's basically it. Pretty simple. Only 2 batch wires that were needed. This wouldn't be needed anymore. Was a lot of work to design this, but I'm very happy that I have this, because that allows me to load programs and files that are bigger than the main memory or bigger than the EEPROM. And this is very, very useful. Okay. That's the wrong one. Let's get back to this and have a look at the last board, which is this one here. So this board is the video board. This has a V9958 video display processor on it. This is supposed to let me use this system completely standalone by providing, for example, text output to a CRT, and this way I don't need a PC anymore as a console, serial console. This has, it's a bit funny, it has 3 banks of memory of 64K each, so it has triple the amount of memory of my CPU board, which is a bit funny. But hey, I had those laying around. I thought the V9958 supports it, why not use it? Maybe I'll update the CPU board later with a lot more memory. Already I'm working on it. There's a video encoder right here, composite, RGB, and S-video output. Also addressable, selectable offset base address for the V9958. Doesn't have any programmable logic right here because there's only 1 chip to address, and I can do this directly with the comparator right here and 2 logic gates. All right, yeah, that's basically it. These are all the components that this system consists out of. Let's go back to the PC, insert this card again, and let's pull up my screen right here. I'll open another terminal. Right. This is the I like to use it because it looks pretty cool, and yeah, just like the way it looks and feels. Until I can attach a real CRT to this PC, I'll keep on using this one, and I'm running Minicom just as a serial terminal. All right, let's turn this thing on and see what happens. And you can see nothing happens because I am stupid and forgot to attach the serial cable again. All right, let's try it again. There it is. It still had some key in the buffer. Yeah, it's no problem. You can see Z80 monitor V2.1 by me. It does some basic power on self tests. Here you can see the RTC is mostly working. The issue is that the time zone is off because of summer winter time here in Germany. But nonetheless, it works. Technically, this controller checks are not implemented yet. Detecting drives done. So this is my monitor. It can do a couple of things. For example, I can have a look at memory. Yeah. Now it works. I can have a look at memory. Then was the wrong location, memory. That's where I wanted to go to. You can see the start of the ROM. We can have a look at the start of memory, which resides at this location. There's a lot of data in here. There's the buffer for the input, command line input. There are the parameters for the file system, the interface and stuff like that. I can also go back further into memory at 800. You can see there's nothing there. And I can use the monitor to add bytes. I type exclamation mark starting address, and then I type in the bytes I want to store. And if I now have a look again at 80, you can see there is the data that I've entered. All right, I'm back. Sorry, I've got interrupted the first time. Now let's continue. I've restarted the computer. I've shown you how I can access memory, but that's not all, because unlike the 6542, for example, the Z80 does not have memory mapped I/O. So this means we have the complete 64K address space available for memory, and we don't need to occupy addresses for I/O. We have a completely separate I/O bus, if you can call it like that. If we take a look at the schematics, you can see we have those two pins, mReq and IO-req, which means memory request and I/O request. So we can access 64K of memory, and if we assert this pin to low, if we pull it to low, we can use the I/O address space, which is 8-bit only, 256 bytes or 256 individual ports, which is plenty for what I'm doing here. But that means we need different commands to do that. And I have those commands implemented. It's called pin. Let's see, pin 40, pin F0 is occupied, I think, by the PIO for the hard disk or a CF card. I can use Pout to write to the IO bus, for example, 0000. Now I've written the byte 00 to address 00. I can also break my computer by writing 00FF, and now it won't work anymore. I have to reset it. The reason for that is that at 00, there are those two flip-flops, and those two flip-flops select the mode, the memory map. So if I set this to FF, I shadow the ROM and set it to full 64K of RAM, and therefore my monitor won't work. Now I have two more commands for accessing the I2C bus. It's IN. I can specify the device address 00, for example, and read 1 byte. I get a bus error because nothing is at address 10 and it does not respond. I can access D008, for example, and this reads out the timer IC, the RTC. I also have a tool for that. It's called date, which reads it out and formats it in a nice way. So it's actually readable. I also have a tool called setDate, which I can use to set the date. No, I messed up because there's no way to exit it yet. And I have another command it's called IOut, for writing to the I2C bus. And I can just specify the name and then write data to it. For example, now I can't write anything to it because there's nothing at address 00. It works similar to writing to memory. Memory, as you might remember, memory was just exclamation mark, the starting address, and then the sequence of bytes I want to write to memory. Yeah, that's basically the same. And there are some more commands, like for example, disk1, run or jump, not run, jump or call, which work almost identically. I can use this to execute a program at a given location. 0000 would restart the computer, same as the reset command. And yeah, there's one more command, clear, to clear the screen. Sorry. And these are the basic commands that I'm able to use. Now, if I want to use access the disk, there are some things that need to be done. First of all, I need to insert the CF card, which already happened. Have to reset the system in order to detect those cards. You can do this with reset or the physical reset button on the front. You can see it says detecting drives, done. And I can use the command lsdisk to list all the disks that are detected. Right now I can only detect one disk because I still have to write some kind of drivers or driver capability into my monitor, which I haven't done yet. So far I can only access one disk, and I can select it with the disk E. Now drive E selected, you can see the prompt has changed. My monitor is a mixture of DOS and Linux. Yeah, it's a bit strange, but it's okay. I'm fine with it. It's my computer. I can do whatever I want with it. Yeah, you can see a directory listing of the content of the CF card. The file system on the CF card is FAT16, so I've implemented, or FAT32, I think it's FAT16. I've implemented it in BASIC, not in BASIC, in assembly, which was a painful experience. I wouldn't recommend it, except you like pain and you like to suffer, then go ahead. I'm not very proficient at assembly, but you can see I got all this stuff working. It's not beautiful. You can look up the code. It works, but it's not beautiful. Hey, but you can traverse through directories, for example, navigate into folder and see what's in there. You can go, for example, in another folder and then to another subdirectory. So the limit is pretty much only the length of the path, which is limited to 256 bytes at the moment. Don't think I'll ever need this with this system. And you can also now run programs from the disk, which is pretty useful because you don't have to build everything that's not fundamentally required for different programs or operating systems into the ROM. I can just put them onto the card and then run, for example, helloart.com, which is a reference to another YouTuber you might know when you're watching this video. Only recommend him, makes nice videos. So helloart.com, hello world. It loads the file to a memory location, then executes it. If we now take a look, for example, at memory 800010, we can see the programs here. There's file header right here, and then here the program is starting. I also started writing a disassembler, which does not work completely. Yeah, it does the first four instructions. These are correct, and then it fails miserably. And yeah, it's all right. I'll have to fix that later on. So, and I can also use load bigger programs, for example, BASIC. And the thing with BASIC is I want to use the entire 64K of address range for RAM, or as much of it as possible, and therefore I have to shadow the ROM. And what this program is doing, it's first loading another program that I wrote, which loads BASIC into an address in the upper part of the memory. Then it shadows the ROM, copies BASIC to the start of memory, then jumps to the start of memory and starts executing BASIC. And we can run this by typing run basic.com. You can see it was loading BASIC to hex 8000, shadowing ROM, then it copied it over to 000, and now we have BASIC right here. We have 57k of kilobytes free, not kilobytes, but 57,577 bytes free. I don't want to calculate this in my head. And we can run some basic stuff. Hello world. 20, go to 10. Which is pretty much the only thing that I've ever written in BASIC. Yeah, there we go. I have to reset it to get out of this BASIC interpreter. Okay, that's all that's to it. We might have luck and have BASIC still in the memory, or at least the start of BASIC. Yeah, there it is. It's still in the upper part of memory because it hasn't been overwritten by BASIC yet. So if we type 8040 again, we are back to BASIC. Let's reset and we are back to my monitor. Yes, that's all this thing can do so far. I'm still working on different programs for it. Yeah, but so far I'm pretty happy. I'm still working on getting the functionality right to a disk as well, creating directories, creating files. There's a lot of stuff I want to do, for example, getting CP/M to work and running games on it, getting rid of this terminal and implementing the VDP, Video Display Controller, and PS2 interface to be able to use it completely standalone. These are some things that I plan on doing in the future when I have time for it, and I'll keep you updated. So far, thanks for watching. Hope you enjoyed it, and it maybe motivated you to do something like this yourself. And yeah, I would be happy to see you next time. If you like this video, leave a like, and yeah, if you want to see more, feel free to subscribe. And yeah, I'd be happy to see you in the next video. Bye.